We have the next address by Ajay Sethi and Prateek Nagras. They'd be speaking about Robotics Application Stack, building in scalable, extensive applications using ROS2. They'd be highlighting Robotics Application Stack as RAS as a framework for building scalable robotics applications using ROS2 with a focus on remote science laboratories. It will also demonstrate how they enable automated experimentation through the virtual workspaces and workflow engines. Over to you guys.
How do you start it? All right. I think this works, so I'll continue to use this. So jumping all the way from the protocol stack to the application. So a big jump, but hopefully, what's this? Okay, got it. Thanks. All right, so never mind. I have to stay here. Okay, so I'm going to talk about the robotic application stack and how can you build ROS applications. So first, let me start by team because if we're running out of time, I don't want to miss the contributors. Starting around 2 years back, Bharadwaj, Kaushal, and I, started thinking about how can we build applications, robotic applications. Actually, we were thinking about what we call open science stack. How can we get the science labs on the cloud? Right? So that's basically the problem statement that we had. Three of us, Kaushal is, I think, I don't see Bharadwaj, but Kaushal is definitely here. So you guys can catch us. Then we got two very, extremely good engineers. They run a AI development studio. Yeah, so we got to. That's okay. That's okay. So we got two Karthik and Deepak. They run a company called Deep Clarity, which is an AI development studio, and they build Gen AI applications as well as especially the vision related applications. So those two. Then next, we got very strong team in robotics, and I think you know them obviously. Acceleration Robotics is one of the organizers of this event. I will have Prateek talking about the actual the code level details shortly, but Alok and Harsh have done a lot of work to implementation work. And then finally we have three engineers or three researchers or research engineers, applied researchers. There's a company called ARCnet, ArcNet, which is actually an initiative for applied research. It's run under Art Park, one of the organizers of this event. Right, and that's basically, they're trying to basically mimic what Stanford Research Institute did in terms of applied research. So if any of you is interested in solving real world problems with a research mindset, you can reach out to them. That's basically the context. But let's get on to the real content of the talk. Actually, before I move on, the work has been supported by Art Park. So that's, one of our supporting organizations. So, it's also sponsor for this event. So, so I think it all comes together here. Right. So this is normally when you talk to people, first thing that comes to people's mind when you talk about robotics are these kind of images. These are from automotive industry and from the electronics industry. These are the two areas where the maximum number of robots have been deployed in terms of the absolute numbers. The next thing that if you ask people, okay, what else is robotics? The thing which comes to mind is the robotic surgery, right? Becoming very popular nowadays, right? Then if you prod a little bit more, you start talking about things like warehouses. Of course, a lot of warehouses are using robots. Amazon, Kiva, in India, gray-orange robotics. So there are a lot of companies which are in the warehouse management, right? But as you look around, actually the robotics is now becoming pervasive. Whether you look at chemical industry, whether drug discovery industry, robots are basically coming in all the places. The interesting thing is, if you really look around, in terms of the revenue, not in terms of number of robots deployed, the maximum revenue, surprisingly, at least surprising for me when I found out, is actually in medical robots. Right? So that's a 27% of the market. The second largest number is actually, as you can see, domestic services. And that is, when you think about that, this is the thing that you will think about, right? The, Roomba, right? So that's the second largest, right? That's in terms of revenue, right? And then comes the one which is actually the maybe most talked about, but actually it's maybe not even the second, it's maybe the third in terms of the value, in terms of the revenue that's in. Right? These are typically older, I should say, not old fashioned, but older technologies which are in automation world, where the assembly line is very set, and you basically have a welding robot or a painting robot, or all various kinds of things. The world becomes very, very interesting when you start looking at the service robots, right? Service robots are basically found in medical industry, domestic services, logistics, agriculture. These robots operate in the worlds which are, in the real world, right? Which are basically therefore not as structured as the assembly line, right? And they have to handle a lot of diverse objects. Right? So that's basically the thing. And because you have such a complicated environment in which you operate in, the applications you develop are more sophisticated, right? It goes without saying. But I'll go more into this and tell you a little bit more about it, right? This is the example. I think some of you would have met, one of the participants here at NX Construction is in this business. But basically, if you look at that, this is a service robot which is doing painting job, right? It has to have a business logic in the sense of it needs to know that it should paint the wall but not the doors, skip the doors and the windows, right? So that's basically it. Obviously it has to navigate the workspace and avoid the obstacles and all that, but there's a business logic that it needs to understand, right? So that's basically is obviously enabled by ROS2 because it allows you to have a device independence, so robot independence way, hardware independence way of doing these things. But if you start looking a little broader, I need to look like this. Okay, so if you start looking broader, there is in the service applications, you see that there are workspaces which are a little more general, right? So between two labs, for example, you will have a different layout. So you have to understand the layouts, right? So the good thing is, if you look at the professional spaces as opposed to domestic spaces, there is some structure to the space. Unlike your house or an office space, there is some structure to the space, right? So the applications you write have to take in the parameter, the layout of the workspace as a parameter. Right? When you write an application logic, you have to be prepared to operate in different kind of layouts, possibly, right? So that's one. And at runtime, when you actually generate your, the motion plans or trajectories, you actually revalidate them. You cannot statically generate them because the work environment might have changed a little bit. So that's one complication that gets added when you are working to develop applications for service robots. Look at another example. Let's say a simple instrument like a centrifuge, right? But there are many, many different manufacturers of centrifuge which have slightly different layout, slightly different configuration of the instruments, right? So if the way you insert the test tube, the way you press the button, the layouts of the buttons are different. So the application has to think about, or the application developer has to think about how they can abstract away some of these details, right? So that they can work across different instruments. Or it could be more sophisticated instrument. This is a pipetting instrument, which is automated in itself. But as a robot, you have to operate it. You need to know, which buttons to press and how to operate this thing. Right? So the implication of this is that you have to understand how you can abstract away some of these low-level details which are dependent on the workspace. Right? So that's the number 2. Right? And number 3 is, and the last one actually, is the fact that the real world, in the real world, there is the objects that you're operating, right? They of course, there's a wide variety of objects, but also that the logic that you have at a given step depends on what happens before. So at the bottom, you see a typical pipeline which is used in drug discovery, right? So it's the first few phases of the drug discovery pipeline. What you do in the last stage, which is a plate reader, decides whether you want to do one more iteration of this application, this loop, or you want to finish it, right? So if you have not got the results, so let's say you're doing PCR testing for COVID virus, so you have to do cycles, and you have to keep iterating till you find a certain load, right? So the number of loops depends on the application logic. It's the business logic in some sense. So that's where it becomes interesting, because these kind of tasks are typically known as long horizon tasks, and they require robotics applications to have much more fault tolerance. Right? So that's basically the 3 steps. These are all the requirements you have to think about when you start thinking of service applications. Right? So then the question becomes, how do you do it? Because there are so many variables, so many things that can keep changing with, right? So really what you want to do as a developer is to have ability to write the application once, but make sure it can run anywhere. Right? So that's basically what you want. Write once, run anywhere. I think we have all heard that before. This is the term that has, long back, I think going back to Angelo's time frame, was popularized by Java, 1995, 96, that kind of time frame. So that's basically what Java did, gave this ability to write once, run anywhere. And that's really what got the cloud computing started. So that is the base. That's historically, that's how, we have come to a point where we have now, things running on cloud and on your phones, wherever, right? So you can run it from anywhere, right? So that's basically what we have. Now, what's the magic that Java did, right? So the magic that Java did was actually break it up into 3 steps. So if at the top you have Java programs, that's the Java programming language. Next level, they defined a JVM, a virtual machine, so that it abstracts away all the different details, at the lower level. So that's a one machine that you have to understand, and then you can write your applications. At the next level is a JRE, Java Runtime Environment, which basically takes care of both execution as well as maintaining the runtime state. Right? So that's the second part. At the bottom is the OS interfaces, which is what really maps what your application is to the low-level details, right? And that's what allows your one program that you write. Python, everything is also following the same philosophy. So this is what allows you to write one program, but it runs on different kind of operating systems, different kind of architectures, right? So if we mimic this, right, we get this, right? So I'll go back again. So the same 3 layers, I can go back, yeah. So same 3 layers, JVM, JRE, OS interfaces. You can basically map them to, when you start thinking about robotic applications, in terms of workspace abstraction, top level, workspace engine at the next level, and the robotic interfaces at the bottom level. Right? So it's the same thought process, but basically mapped onto the robotics world. Right? Now, what do these 3 layers correspond to? So the first one, the workspace abstraction, is what allows developers to specify the application logic and make sure it is written in a high level. You don't have to worry about what exactly instrument is there, which robot is going to be there. You write your application logic in terms of business logic without worrying about the low-level mechanics. Right? The next level, the workspace engine, then takes care of running the program. It basically, actually the first layer also takes care of compiling the program and all of that. And the next level takes care of running the program. And running the program in this case means sending the instructions down to the next layer, which eventually sends to the robots, as well as maintaining the states of the engine. Right? And the bottom layer is equivalent of OS interfaces, which is the robotic interfaces, basically a wrapper around ROS2. Right? So that's basically. So the bottom is a ROS2 wrapper, but the top 2 layers are the application logic layers. So this is basically what we call. So this is what we call open science stack. Right? Oops. Okay. All these layers. Now, if you take only the blue highlighted things, these are the robotics elements of it, right? So the layer itself, what we want to do is take out the robotics elements of it, and that is what we call robotic application stack, right? So that's the context in which we have basically developed the RAS, which is really a layer above ROS, and so that anytime you're thinking of writing an application, we like you to consider RAS. And I'll let Prateek actually talk about the actual details of how we implemented it and how it can be used by all the developers.
Just forward. Yeah, thank you. So now I'll talk about the robotic application stack from a developer perspective. So what is a typical developer workflow? When you want to do a task, what you do, okay, you define what is your application. And then you set up a simulation environment. You then write the robotic ROS interfaces, figure out, okay, which are the sensors, which are the robots that you want to use. You test it in simulation, and then you run it on the real robot. And then you have to work on the feedback. Depending on what goes wrong or what goes right, you make changes and you follow this cycle again. So while doing this, what are the challenges that typically a developer faces? So first thing is, when you're doing this, there's lack of robustness, because when you're writing a program, you don't really have the time to think about all the edge cases, what will happen when it goes wrong. You just build your application and then figure out, okay, this is going wrong, let me add a fallback. So there's lack of robustness. This lack of modularity, again, it's a typical developer, what do you say, thought process that let me just get it working at first and then we'll see about, if I want to add something, I'll think about it later. And many a times you have to start everything from scratch again. So lack of modularity is one of the problems. Lack of extensibility, building on modularity, it's mostly similar. Then there's lack of digital twin and simulation. So when you're doing something, you have, okay, workspace in mind, you put that in simulation and you write your whole program. Then if there's some changes in the real world, you have to then redo the changes in the simulation, repeat the process. Then there's a maintenance overload as well as lack of task and robot agnostic. Okay, if you write the program for one robot, there's no guarantee it will work for a different type of robot or a different type of instrument, different type of sensors. Of course, ROS helps there, but that still needs to be taken into account when you're developing your program. So this is the video of what we have developed. So let the video play. So you can enter a prompt. Okay, so pick up an empty beaker, place it at a position, pick some other beaker, pour water into another beaker, and place the beaker somewhere else. So you could just put what you want to do in your natural language and wait. You click on load experiment. So we have a natural language processor which is interpreting what you said and converting that into a structured text so that the robot understands. You can see it generated a config file with what you want to do. You want to go to a pose 1, you want to grasp, you want to go to a pose 2, you want to pour, you want to place something, go to another pose. So it will just generate all those sequences automatically. And it will run in simulation, it will do the path planning, it will do the grasping action. And once all of that is done, it will transfer that to the real robot and it will execute that. So here you can see it in simulation, it's doing the planning and the grasping actions. We don't yet have a link attacher plugin available in Gazebo. I'm not sure if Yadu is here, might be able to help us with that. So that's why you can't see the things are actually being picked in simulation. Our team is working on adding that plugin. You can see it picks up the beaker. We have a pour action, so it pours the water in another beaker. And then it can just place the beaker. So this is the demo application that you saw. Now, how does this actually work? So our architecture is in has 4 different layers. One is the application layer. Second is the simulation layer. Then there's a communication layer and the execution layer. So let's first look at the application layer. So in the application layer, you have the option to upload your task in a text format or through an NLP. So you can just you can have it in a natural language. It will do an NLP API call and convert it into a format that the robot can understand. Then we have something called as an asset manager, which has all the details of the machines, equipments, and the poses of all the instruments which are there in your workspace. It fetches the information from there and generates a YAML file, which is the input given to the behavior tree. So the application layer basically has the application logic workflow. It is modular and it's abstracted from the lower level processing. It has integration with the behavior trees. The simulation layer now takes in the behavior tree. It executes that behavior tree. Let's say you do a pick action, you do a place action. Every action is recorded. So you don't need, when you are transferring this information, what you're doing in simulation to the real world, you don't need to do the path planning again. You just need the trajectories that have been executed because they have already been verified, and those need to be executed on the real robot. So there is a trajectory recorder which will record all the trajectories and the sequences for it, and it will be passed on to the AWS server. So the simulation layer takes care of the simulation as well as the safety validation. It has a behavior tree manager. I'll talk about that in a bit. Then you can deploy it to the real robot, so a behavior tree generator which is passed to the real robot. And then you have visualization, you have synchronization between the sim and the real robot. So the execution layer, so there's a communication layer in between, which is basically AWS. We are uploading the trajectories as well as the sequence of actions and the behavior tree to an AWS S3 bucket, using AWS IoT to share the link which is generated, and the execution side robot just pulls that and executes it on the real robot. So execution layer is basically just taking care of the real-time execution, but the behavior tree there includes all the fallbacks, any retries, all that is necessary. So this is the typical workflow from a point of view of like how the things work. The user gives input. There is an asset manager which has all the information about the workspaces. There's a Batman, which is a behavior tree automated manager, which processes all the information, generates the behavior tree. Then there's a launch file, so in the config file, you have defined what are the poses of where things are. So that config file is used to generate the Gazebo world automatically. So even if you change things in the real world, you can just change it in the config file, and the world will be automatically generated at runtime when you run the simulation. Then you have an executor which executes the behavior tree. You have the trajectory recorder service which is recording the successful trajectories. There's a behavior tree sender which sends it to the real robot. IoT sender is the one which is actually sending the data through AWS. And everything of this is running on cloud. So you can be sitting anywhere, you can be running this, and you can just connect this to a real robot anywhere in the world, and you can execute that. So the data is received and it is executed on the real system. So while building this, we developed a very unique, you can say, piece of code, which we called as Batman, which is behavior tree automated manager. So what we observed is behavior trees are like really great at abstracting behaviors and making things modular. So what we wanted to do is abstract the higher level from the lower level actions. So we have when you are doing a sequence of actions, you cannot, you will have to write the behavior tree every time. So what we do is the sequence of actions which are generated, the behavior tree is automatically generated based on the sequence of actions, and the fallbacks and the retries are automatically added to it based on the type of action it is. So for example, on the left side, this is the behavior tree which is in the simulation where you need to go to a pose, you need to switch on the gripper, you go to another pose, you want to switch off the gripper, and you want to rotate. And this is the thing, this is the tree that is run in simulation. Now, what our script does is, it goes through this and it maps what is the simulated action to the real world action. So you have some, okay, for movement, you have a piece of code written, for pour action, you have a piece of execution code written. It maps it to that. And let's say for pose, you want to do 3 retries, maybe the velocities weren't correct. So it can adjust the velocities in the fallback node automatically. For gripping, you need to sometimes grip multiple times because the first time it might not have been successful. So it can automatically add retries depending on the type of action. So you have the flexibility depending on your type of action, what fallbacks need to be added. And then that behavior tree is basically the one which is executed on the real robot. Now, who should consider this robotic application stack? So this is something that will simplify your development. It is also something that can be used for scalable applications. So you don't need to worry about, okay, is my code modular enough? Is, like, if things change, how will I have to modify a lot of things? No, you don't need to do that. The stack takes care of everything. What you need to worry about is your application. There are templates available where you can just put in your actions, like we have move, pour, rotate. It could be operating an instrument, and you can just put in your actions there and it will work with the stack. This is also good for distributed systems as well as dynamic workspaces. Like I said, you can just update the config file. It will generate the Gazebo simulation and accordingly the real world execution as well. It offers multi-robot support, of course, because we are using ROS2, we are using MoveIt2. So the execution on the simulation side as well as the real world side happens with MoveIt2. So you have the option to change the planner, use Octomap. All the features that you have with ROS2 are still with MoveIt2 especially are all available to you. And for efficient testing, so you can quickly iterate over different kinds of applications, and this can be used for quick efficient testing as well. So what's next? So after this, what we plan to do is add vision feedback, because even if things run well in simulation, even though we are just running the trajectories in the real world, there are some times which there are going to be times where the execution is not completed properly because for some environmental factors. So having a camera or a vision feedback to know if those tasks have been completed is necessary. And also we have a system. So let's say when you run in simulation, you run it on the real world, maybe after the third step, it stops. So there is a sync always between the real world and the simulation. The simulation is always updated with the real world system. And if you stop at step 3, if something goes wrong, you can regenerate, you can fix that thing in the real world, and the system will regenerate the trajectories from the third action, and you can continue your application and testing just from that action. You don't need to restart everything from scratch. We also plan to add AI-based inversion of control, so the robots can, the AI can actually manage the flow of the program when deciding when to call what component at what time. Plan to add CI/CD, of course, that's pretty important. And we also want to add support for multiple robots, multiple grippers as well. So what are your thoughts on this? Do you find this is interesting? Would this be useful? Okay, but you haven't heard the best part yet. So this is fully open source. So you guys are open to contribute. So I have heard many people come to me and ask about how can we contribute to ROS. So whatever you heard, everything is open source. It's available on the ROS2 repo. You can scan the QR. You can find all the repos there. You can test things on your own. You can email on info@opensciencestack.org if you want to contribute. You can meet any one of us who are here on how you can contribute, and we'll be happy to work with you. So yeah, that's it. So thank you. Yeah.
We have a few minutes, so if you have any questions, please go ahead, ask us. And I think I'll request since we have time, I'll request the contributors to also please come on the stage so that we can at least, you guys know who all have contributed to this project. And we love more of you to join us next time, but at least the ones. But go ahead. Yeah, go ahead. You ask your question.
Hi Prateek. Thanks for the nice presentation. So my question is, during the demo, you entered some coordinates, right? So how does the user know that what coordinate frame the robot is operating in? What is the right coordinate frame?
Yeah.
And probably an user would not want to know that much precise information. Like it needs to be a little more user friendly, I feel. So
yeah.
Your take on it.
So see, there are two options. So in the basic way is whenever you're setting up a workspace, you would need to know you will need to fix your origin and have all the other instruments or whatever you are operating with known with respect to that origin. So if that is known, then you can put that in your config file. That is the basic way. The second way is when I mentioned vision feedback. If you put cameras in your work cell, you can, to start with, you can put AR tags on each of your instruments so that they are unique. So the camera can find out where those are, and it can automatically fill in the config file with the positions of that object. So we have designed the system in a way where even that is directly possible. You don't need to rewrite a lot of things. So keeping the AI vision feedback in mind, we have already designed it. So that is something that will be added soon, or we'll be happy if you guys contribute in adding that part as well. Any other questions?
Yeah, hello. My name is Sudhanva, and the question that I have is that let's say you are using the natural language for generating the behavior tree, right? How are you intending to handle the error handling and the recovery of the errors?
Just
Let's
for the NLP part.
no. From the NLP to the execution. Let's say the arm is picking up a beaker, and the beaker falls down. In such cases,
Correct. So, we are using behavior tree for that specific reason that you can add your own fallbacks pretty easily. So, like I mentioned, like right now we have an option. Okay, we can add retries. If we check, the gripper will have some sensor which is just checking if it has picked or not. If not, it will just retry. If in 3 tries it does not pick up, then we need to have a fallback to go back to, let's say, the origin, and then maybe have a camera sensor checking if the object is actually present there or not. So if nothing works, then you will have to have an external agent fix those things, that something's wrong, the robot is not able to pick that thing, do something about it. So the granularity on how you want to add your fallbacks is up to the user. So when you're saying, like in your example, if it cannot pick the beaker, we have few options. Is we can have a camera checking if it's actually attached to the gripper or not. We can have sensors on the gripper to know if it's attached or not. If both of these fail, then you can have another fallback that, okay, the object wasn't picked, so I can't continue with my experiment. And that is where you stop. And if not, if you have other ways to handle that, you can just add that according to your application.
okay. So, are you also intending to have the diagnostics integrated?
Yes. So we do have some logging already enabled. So when you test it out, you will have the logging, like because the real world execution and the simulation is always in sync. All the data, like whatever changes are in the real environment. So when the beaker is changing positions, all of those happen in simulation as well. And we are recording at each and every step of execution the metadata in the environment.
No, that became the logging part.
Yeah.
So the doubt was for the diagnostics.
Diagnostics we haven't yet added. That could be, we'll be happy if you are willing to contribute and help us out. Right now we don't have diagnostics in this.
Thank you.
Okay, hi, nice presentation. So I would like to know what is your future plans to incorporate other type of robots? Say, I think you have covered the manipulators.
Yeah.
So what about, say, drones, the AMRs, those kind of stuff? How do you like plan to scale this application stack to a broader space?
Yeah. So we have written the stack in a very modular way. Once you see the stack, you will understand that, okay, everything is separated out. It's modular enough where you could try to even integrate AMRs and drones. So we honestly haven't tried that yet. Our focus has been with robotic arm and robotic arm applications. But if you want to, we have something in pipeline where the robot arm is on a base, AMR base. That is the application that we have thought of. We haven't yet planned on how we approach that. But I mean, we'll be happy if you want to actually work on that part. We could brainstorm and figure out how that can be done. But it is possible on this stack.
Yeah, you just mentioned that the output from the NLP layer goes to a sim layer, and the planning happens there, and then the motion plan is then sent to the real robot. Doesn't this flux adds? Doesn't this have an issue with the real-time applications where you want to modify or do things real-time, or there's some other robot which actually demands those real-time motion plannings, but you cannot do that because there's a sim layer in between. So how are you planning to mitigate that?
See, think of this as a development tool. Firstly, this is a development tool. When you are starting out, you want to implement your application. This is where the sim layer will come in. That is where you want to first test things out in simulation. NLP, what it is doing, it is instead of you having to manually input it, it's using the natural language processing to just convert that into the format that the robot can understand. Once the simulation is done, we just record the trajectories and the actions, and it generates a behavior tree for it, and that is the one which is executed on the real robot. So that, and only thing that is connected to the simulation is the data flow from the real world on what things are happening, so that the simulation is in sync. The simulation is not controlling the real robot once you have fixed your application. So this simulation to real robot to again simulation, this is in the development. It is the iterations that you do, but once you fix that, it is just the execution. And if something goes wrong, you can have that data in simulation and you can try to figure out things from there. Okay, I think that should be it. We are already out of time. So thank you everyone.